Hi guys, so today I wanted to share another problem with you, which I was solving yesterday and found quite interesting. It's a bit on the massive side, but I hope that you will find it interesting as well, regardless of it being a little bit mathematically involved, I guess, but not much, don't you worry. So this problem comes from a recent global rounds. It's problem F. So somewhat complicated, but remember that global rounds have 9 problems, so that is kind of like in the middle of things. And it is yet another moving ends problem. So you may be familiar with problems where ants move on some lines, and for example when they intersect they somehow change their directions. If you if you followed mathematical inputs for some time, on at least on the international level, then you may find this situation familiar. So, but it's not required to solve the problem in any way. So in this problem, Telepanting, we have Telepanting, easy pun, in case you have not noticed. So in ant, we only have one ant, and it moves on the real line with constant speed of 1 unit per second. It starts at 0 and always moves to the right, so its position increases by 1 each second. However, there are n portals, the ith of which is located at some position xi and teleports to a position yi that is before xi. So the ant is trying to move to the right, but some teleports may take it backwards. However, they can do that only when they are active. So the portals can be either active or inactive. The initial state of the ith portal is determined by Si, so that's like another variable you get in the input. If the portal is inactive, like in both cases, when an ant moves through the portal, when an ant reaches the position of the portal, I should say, the state of the portal changes, but also it may, if it was active, then it will teleport. If it was not active, then it won't teleport. So, and the question asked is how long it will take the ant to reach the position xn plus 1. So pass all the portals so that it will be no longer affected by them. Obviously the answer can be well large if we just keep teleporting. For example, something like nested teleports is, I believe, a very long route to pass. Something like this may take a lot of time, so we shall compute the answer modulo. And also we have a lot of portals, so yeah. And then just your regular input description. Interesting thing that they tell us that you can show that it happens in finite amounts of time, but it may or may not be immediately obvious why this happens. And I mean, this problem is 2200 rated, so not as easy, but also not so complicated, but definitely not very easy. So first thing that I wanted to figure out for myself is why this process takes finite time, because obviously you want to understand why this happens before you solve the problem, because otherwise by finding a solution you eventually will prove this, so why don't prove it straight away. So what I was thinking is we can define a state to be, well, obviously states of all portals should be included, so S is definitely in state, but also current position of the ant, which will denote by I don't know, X. So this is a state. Now the process is completely deterministic, So like we have very specific edges, either of the type like x plus 1 s, or I don't know, like x plus 1 s prime, because we passed through some inactive portal and changed to active, or we have some other edges. Either way, like we can't have two. Like each state uniquely determines the next state, the position at which will be the very next second. And because of that, you can also see, like, because of the special structure of our process, like it does not involve anything, or rather I should say, because of not so complicated structure of our process, each state also has like a unique predecessor. If you are currently in this state, then you know, like, okay, I either got teleported here from another location, right, if this is a portal location, or I just moved from x minus 1. And depending on the situation, you can see what actually happened. So yeah. So imagine that given such like conditions, you get a cycle. So like in degree and out degree. We've shown that in degree and out degree of each vertex is exactly 1. So if you have a cycle, then it means that it's not reachable from our original state, because our original state is an infinite chain that goes all the way to negative infinity and s as 0, let's say. Because like we started before all portals, we may as well assume that it goes back to infinity, so it's not a part of a cycle. And there are some teleports, and then we go all the way to positive infinity and then something. I can define it by st, meaning that this is a terminal state. So okay, cycles out of the way. It's natural to start wondering what a terminal state is. So like what will be the state of all portals once we pass through them? And you may notice immediately that like if I passed through some portal, so there is like a portal here and I'm here, and this portal is active. And in fact, all portals here before my position are active. Well, why? Because like originally I was here, right? At some point I had to cross this portal. Let's consider the last such time that I crossed the location of this portal before I got here. Like, you may be wondering how I got here. But the reality is, like, if I passed through a portal and it did not teleport me, then there was nothing to wonder about. It was turned off before I crossed it and got turned on because I crossed it. So one of the key observations is that like this structure, that once we pass through a portal, it must be turned on. Okay, that does not exactly tell us much in terms of computing this distance. So then I started wondering like how we may even approach this thing. So basically, my idea was that in a way, it's very hard to compute the distance if you don't know how many times each portal was used. Like, it's not clear if it's even possible. So it is very preferred to have something, like have some variable. We'll call it dp for now, and you will see very soon why. So dp of I is the number of times ice portal was used. Why? It is important. Well, if we know each dp of I, then the answer is, I believe, like xn plus 1, because like we have to cover this distance, but then we may have some teleports backwards. Now teleports backwards don't count themselves, but what counts is then that because we had a teleport, we have to manually walk back. So, except this thing, we also have sum over all portals. How many times they were used times xi minus yi. Because that's like every time you use a portal, it means that the distance to your destination increases by the span of this portal. So yeah, values dp of I are clearly very important. So our first idea is dynamic programming. And once again, like the same as with the previous problem, this problem has several ideas to it. That's why I wanted to show it to you, because it's not like one observation that you can find or miss. No, there are various aspects to this problem, and even if you notice only one of them, that will be already educational. So in a way, like those good problems, they increase our learning rate. Because even if you don't like watch entire video or don't solve the entire problem, you still can benefit from it by finding several ideas, some subset of ideas that are necessary to solve the problem. That's why I choose this problem. So I was solving some more problems yesterday, but I think that this one is the nicest of them all. Okay, so once we know this, like well, originally you don't think about this as a DP. You think about this like, okay, I just want to some count of I, and then I will use this count in my sum. Right, so DP is, to be fair, not an original idea. Rather, you want to compute these numbers Ci, and then you start thinking, how can I compute them? So our focus will be on computing Ci next. And we will use the observation that after, like whenever we are at some location, all previous portals, and this of course denotes the X position of the portal, not the Y position. So all the previous portals are active, turned on. So in particular terminal state, we already figured out it is just all portals are turned on, to answer the question that we posed to ourselves earlier. Okay. Now, because of this structure, like you see your states, they have some prefix of portals that are turned on. So it is natural to try to compute values in some order. That is either this or this. And well, once you try computing values forward, like it doesn't seem very possible, because teleports can, like, when you are here, you already know all information about these teleports. When you are here, it's hard to predict what will happen, Otherwise, if it was easy to predict, then there would be just a simple formula for this that does not involve anything like smart, but that's like on a meta level. So it is most likely that we want to compute dp backwards. This is an idea that is more mathematical than programming, I think, but like I would state it as like solve the problem backwards. So that's if you can't do something in the original order, we may want to approach it. Is specifically applicable to problems where you have a process that's something changes. The process has a state in like you can both predict what will happen in the future and like understand what happened in the past. So in such processes, trying to solve the problem backwards, I guess backwards. It may be very helpful. So in our case, like what we see is like we will try to compute dp of n-1 effectively, or provided their indices, I should say dp of n, but in our implementation it will be of course dp of n-1. This is like how many times the last portal was used. How many times? Well, like it's impossible that anyone will teleport you here so that you can walk through it again. So like you only walk through here once, then it may teleport you back. Then after you walk the second time, like it will be already off, so it won't teleport you back. And there is no one to teleport you from here. So it gets used at most one time. And we know that in the end it's on. So in fact, it gets used if and only if it was originally active. Because we pass either one time or twice. And in the end it's on. So in the end it's on. So here it was off. Here it became off. So if originally it was turned on, then you used it twice. If originally it was turned off, then you didn't use it. You just walked through it. So the use operation is actually only this one, right? I may denote them with different colors. So if it was originally turned on, then we will use it exactly once. If it was originally turned off, then we won't use it at all. Okay, so that was kind of easy. And more generally, like these values are SI. And it will always happen, like no matter which portal you consider, the first time you get to it, you will either use or not use it depending on SI. So we already stated that we will compute dp in reversed order. So we may say like for e from n to 1. We may safely say that we will have like dp of I plus equals si. So if the portal is originally turned on, then it will fire at least once, let's say so. Yeah, so we will use it at least once. But we may use some portal multiple times because we got teleported back. And interesting things happen. So like, let's consider this portal and this portal. So we come here, right? We get teleported back, then we walk through here again. Will this operation use this portal or not? It may, initially it may seem like we can't tell, but remember our lemma. If we are at some location, then all previous portals are turned on. In particular, when we get here, this portal is turned on. So here it will guaranteed get activated and teleport us back to some location. And in fact, this is true for all portals in between. They are all turned on. And at some point, they will teleport us back. So what we should do next is like, we know that for let's say this is I, and these guys are like J's, right? So what we should do is for J in some sets, that we will, let's call it S of I, or P of I, P from portal. So for all J, every time that I's portal gets used means that all portals J also get used once. So we should say that dp of J gets incremented by dp of I. Right? Now there are several problems to this code. First, we don't know what P of I is, but this problem is relatively easy. So like, what are the portals that we get to use again? Exactly those portals that are located between xi and yi. To be more formal, all portals such that xj is between yi and xi. Well, clearly last such portal, like they all end on here, like this one is already out of question. And then you may also have noticed that xi's are sorted, so that makes perfect sense to binary search over them. So we supply position of yi, and they give us the first j that such that xj is greater than yi. And then we update everyone from j to I, j inclusive, y not inclusive. So this set is actually from j0. I can call it from j of I. j0 of I, because it depends on I, up to I minus 1. Now this is problematic. This yields quadratic solution, of course. But then you may notice, so like, let me just make it clear that binary search is definitely a common topic to know. It's kind of obvious when the array is sorted that you may want to use binary search, but it may also be for convenience, just for convenience of, I don't know, generating tests, something like that. I don't know. So it does not always fire, but when the array is sorted, it may be a hint towards maybe trying to use binary search. But this is quadratic, so what are the operations that we are doing? Well, to be fair, like this is point increment. We can do point increments with almost any data structure that you can imagine. This is a range increment, and we can also do range increments with a wide variety of data structures. The way I did it in my submission was by using Fenwick tree. So DP is not stored explicitly, but rather stored in a Fenwick tree. And then we can perform range of dates and point queries, because like technically we need point queries to know what to add, to know the data. So we'll see the implementation very soon, but yeah, general thing, like you may want some data structures, and in particular Fenwick tree. Fenwick tree to help you solve some of the problems, which are not necessarily like about data structures. So this problem like originally does not appear that it has anything to do with data structures, but it turns out that it does. So, you know, like sometimes data structures are useful to optimize maybe certain quadratical operations to n log n when you're doing a lot of such operations. So yeah, with that in mind, let me pull the implementation up so that we can look at it together and maybe find something interesting. So just for convenience, I defined a custom structure to hold a portal. There is not much to it. I could have used just tuples, but I like custom member names, so that's why. I also have my Fenwick tree. It's fairly average. It can be used for segment updates only. Hopefully you know how Fenwick tree works, but in case you don't know, a very brief introduction is that you have an array, and then each index stores some information about a array tree. So this is like tree. It may be different from your original array A that you want to perform operations on. It most surely will be different. So the way tree works, that each element of tree corresponds to some subsegment of A that is uniquely determined. I will try not to tell lies, but I believe that last element corresponds to the entire array. Something like in the middle corresponds to left half. Something like next to last corresponds to the right half. And then they go something like recursively, but it may be a lie. You know, that's Fenwick tree is very simple, but also very like strange data structure in terms of all the bit magic happening under the hood. The way to think about Fenwick trees is, I believe, one of the ideas that I've seen several times is that Fenwick tree is in a way a segment tree where we store only left children, So this is why I decided to draw this picture. I hope that it works somehow like this, but it may be like completely incorrect. So in particular, it may be the case that like this is the correct, this is a correct diagram, but only if the length is a power of 2, and then if the length is not the power of 2, then you kind of cut it. You draw a bigger diagram and then cut it, instead of dividing each ray exactly into 2 halves. So like, it may be not a half, right? This may be not a half, but like so some were there, will be 2 to the power of n, and this position is 2 to the power of n minus 1 or something like that. Yeah, I believe this is more or less how it works, but to be fair, to be honest, I'm not sure. And like, fun thing about data structures is that you don't necessarily need to understand every single detail to use them. In particular, I can tell you for like guaranteed that I don't know how Ukunan algorithm for building suffix tree, I guess, works. But I still use it several times successfully. So yeah, yeah. Sometimes it's good enough to just have a broad idea of what's happening. So like, well, entries contain information about segments, and each segment can be composed of local and segments, so that is generally quick to make some updates. And then to query some elements, you will need to represent, like, again, element is a segment of range of length 1. So like, by combining several segments, you can get longer segments, and to get some segments in between, you may use like I don't know. You may need to use to take the difference. So like, actually, when we update delta from L to R, it means that we update prefix from up to L with delta, and then we update prefix up to R minus 1 with minus delta. Like, so yeah, like it's a common idea to represent each segment as a difference of 2 prefixes. If you can do operations on prefixes efficiently, then you can also do operations on segments inside efficiently, if the operation is revertible, of course. So yeah, but hopefully you kind of know how Fenwick tree works more or less, maybe even better than I do, because yeah, I mean, it's relatively short. So, and again, CP algorithms or any other online resource likely explains the inner workings of these indices, but we won't. So once we have this, we have our Fenwick tree, which I guess was more reasonable to call it DP. Case sensitive. So when we iterate backwards, we update if originally the ICE portal is active. It means that we will always use it. And we update segment from ICE element to ICE element, but that is like, you get to do what you get to do. And then we binary search for J, for J0 of I, if you remember the notation. So we may search up to the end, but what's the point? Like, we will guaranteed search up to ICE position, so it's like a minor speed up, not very important. Interesting thing about std lower bound is that those iterators need not point to the elements of the same type as you're searching for. For example, I can search for an integer in vector of portals by defining my custom comparator function. This is more or less like std sort works with custom comparator. You can also use it in lower bounds. In case you did not know, now you do. Because I did not know it, I kind of expected it, but I was surprised when I typed it and it actually worked. So STL is very powerful, very generic, I should say. Not so powerful, because it doesn't even have fanfic tree, and it needs not to. STL solves different kinds of problems. When we update from J to I not inclusive, with current value of the P of I, because it won't change. We already accounted all impact from further portals, and previous portals can't change the value that I's portal gets used. So once we have that, we'll have to cover this distance originally. Then also every teleport prolongs our journey by this much. So yeah, that's more or less this. You have to use long integers in places. Also, the way I implement fanfic tree, I kind of, like, you may or may not have your own class for modular integers. But I decided that we will just, like, if you update with positive values only, then like all your operations are plus equals only. So your values always stay between 0 and 2 times mod, and after modding operations that get back to from 0 to mod. So in fact this, I believe, is not necessary, and we can just print answer. I guess this is how it works. Let me just quickly resubmit it to make sure that it actually works. Because generally speaking, making changes when you explain something is kind of bad. But at the same time, I want to provide you guys with the most reasonable implementation. I believe that guys in the editorial somehow managed not to use fanfic tree, but they have more complicated DP, and then they also have like, oh, they just have a bit more complicated DP and a bit longer implementation, I believe, despite not using fanfic tree. But yeah, like, if you have it pre-written, definitely use it. But also, in a way, like, it is reasonable to use specifically fanfic tree, because this is how we arrived at the solution. You can see that that got accepted just now. There were also some worse versions that I don't really want to show you. So yeah, the link to code will be down in the description, as well as the link to the problem. So hope you enjoyed, hope you learned something new. So just a quick reminder of what happened in today's problem. We had dynamic programming, we had binary search, we had fanfic tree. We also had a more mathematical idea of solving problems in reverse order, solving problems backward. So when you don't know what will happen if you go in reverse order, but you know very well what will happen if, like, how we ended up here. If you can answer this question efficiently, then maybe try solving the problem backwards. So yeah, today's episode is, I guess, kind of shorter than the previous one, but keep in mind that this problem is only 2200 rated, so very doable for all experts. I want to say that, like, if you're only an expert, it's still doable, and you may learn a lot from doing it. So yeah, strongly suggest to solve this problem, give it a try. Even if you're a specialist, just take fanfic tree implementation, find it somewhere online, and try to use it. Maybe you will find it nice. Maybe you will want a better implementation, which you can always do. So yeah, hope you enjoyed, and I will see you soon, I guess tomorrow, with the new problem. Bye bye, guys.